Good evening, YouTube. Okay, today has been a calibrate-y kind of a day because it's that time of year when we check anything that we use in the hangar, formally record its parameters against something traceable to an international standard, and that is fine. You can see easily how that's done with something like a micrometer. I've set up a 1.5 inch stack of gauge blocks there. I'm going to teaser in with one hand because I'm holding the phone with the other one. And on a standard day, it's been 20 degrees in here all day, temperature's nice and stable, and a Mitre Toyo micrometer, which is relatively new. I expect nothing less than perfection. There we go, on the money. And because my gauge blocks have been calibrated to a much higher standard than I need for this micrometer, you know, in millionths of an inch, and because the temperature is good today, I have no reason to disbelieve what I see. I can trust my gauge box. I can now trust the micrometers and instruments that I've set by them. And I've recorded all those readings for the purposes of, you know, the CIA when we have an audit, and everything's honky-dory. And I've got lots of other sort of master standards in the hangar. It's a bit of a mess. I've got a precision shunt here that we use for measuring currents. It creates a few millivolts drop when you pass current through it, and those millivolts can be measured very accurately on the fluke, which goes away to be calibrated again to a very high standard, a higher resolution than what we actually need for the instruments that we're calibrating or comparing today. So again, it's really important that we have a facility to know that our instruments are good in the hangar. And that brings us on to something like how do we check when we're servicing an aircraft an airspeed indicator, top left there. And we can have a quick look at that. Again, it's about comparison to a master known certain standard. I guess we should first briefly figure out how an airspeed indicator works. In short, it is a pressure gauge, and it measures pitot pressure created in this forward-facing tube with a small hole at the front, and that pressure is called dynamic pressure. It's created by the aircraft moving forward through the air, and it is proportional to the square of the airspeed, and that gives us indicated airspeed. There is a complication because it has to take into account altitude by using static pressure, but we're not going to deal with that today. The basic principle of a pitot tube and an airspeed indicator is that it is a pressure gauge that measures airspeed by measuring dynamic pressure on the front of this head, which is the simplified way we're going to deal with it today. Right, so as I was saying, with pressure instruments, there is another way other than using mechanical instruments that takes us right back to basics, which can measure and calibrate pressure very, very accurately. That's the principle of the YouTube manometer. It's a manometer, it's not a womanometer or a personometer or a gender non-binary-ometer. Although gender non-binary-ometer lives matter. No, I'm getting political now. It is a manometer. I've got here a piece of tube, it's open at both ends. I've put some water in it, and as you would expect, the water level has equalised. Okay, there's some camera distortion there, but the water level is equalised, and whatever I do with the tube, it will equalise unless I put pressure in one end, and then there will be a height difference in the water. Alright, but supposing we know the density of the water and gravity, that height difference represents the pressure that we can calculate. The formula is rho GH, that's the density of the water times local gravity times the height difference between these two menisci, don't know what the plural is. So it's actually a simple process. If we do know the density of distilled water at 20 degrees, and it's pretty well known, and we do know local gravity. You can find that on a NASA website. That's a well-known thing. Not much interferes with that, so we can get a very, very precise measurement of pressure using a very simple piece of equipment. That's what I'm trying to say, I think. And that's kind of what we're going to do. So if I connect one of these ends to an airspeed indicator and raise the other tube up and down, I'll create a height difference here because the water can't flow into the instrument. It's a pressure sensing instrument. It doesn't allow flow into it. So I'll create a height difference and we should see an airspeed. So let's do that. Right, I'm connected to an airspeed indicator here, and there's my water. Now carefully, with one hand on the teflon, I'm going to raise this tube up. I've created a height difference there, probably about an inch, and an airspeed of 40 knots. And if I go up 2 inches, you can see I haven't got 80 knots because the pressure goes up with the square of the speed. It's a non-linear relationship. But, okay, back to equal water level again and 0. Raising up this tube here causes a rise in airspeed. Simple as that. So if we had a really accurate way of measuring this height difference and some decent formulas, which we do, formulae, plurals, don't get it. It doesn't really matter if you don't understand the maths. All you have to understand is the principle that the difference in these two water levels represents an airspeed. We can calculate that. We can use a computer. We don't need to be genius mathematicians. And we can use an instrument which is not susceptible to the mechanical errors of a round dial like this. Wouldn't it be great if we had one? Well, we do. Okay. All right, how cool is this? It's a vernier water manometer. A water manometer because, like the tube that we just showed, it's got water in it. A vernier because it has a vernier scale on the side. Okay, here is the tube at the bottom. Only instead of just being a plain old tube, it is connecting to chambers. Okay, here and here. And this chamber, you can see the water level there, has a needle sticking up, and that needle is fixed and it can touch the bottom surface of the water there. And if we look through a clever viewfinder, which is a mirror looking up at 45 degrees into that water, if I can get my camera to focus down this viewfinder, stick with me because this is such a cool thing, you can actually see two needles. What you're actually seeing is the needle that we just showed in the chamber and a reflection in the underside of the water of that needle. And when that needle is just right in contact with the surface of the water, they will appear to be touching. You'll see later in the video, if they're not touching, you'll see the deflected surface of the water. And if I can get the camera to focus, this is the vernier scale on the side, and that chamber can be lifted and lowered, and the height of it relative to the other one read from the vernier scale. Now, suppose I don't understand any maths, but imagine a clever person. Right, I understand a little maths. But I ain't no Einstein. Some clever person, imagine they'd written a computer program where I could put in the knots, the temperature, the density of water and gravity, and it would tell me how many millimeters of water I need difference between those two chambers. So 40 knots would be 26 millimeters, which is pretty close to the inch that we saw when we did it crudely with the pipe, and 55 knots, pretty close to the 2 inches that we saw, 50.16 millimeters. So now we have, in theory, a method, let's go for 50, to set or to look for a pressure that produces 41.44 millimeters of height difference in the water between those two chambers. 50 knots, 41.44 millimeters of water. Doesn't matter if you don't understand the maths, as long as the computer can do the maths, you can accept this. You can get somebody smarter than you to run through the formulae and make sure you got it right, because it's how it is. It's a fact. We don't need to worry about it. Other cleverer people have done it. All we're worried about is measuring accurately 41.44 millimeters of water and connecting it to an airspeed indicator to create a height difference. Right, here is our very cool manometer, and I have connected this chamber, which is filled with water and currently equalized in level with this chamber by the tube connecting them. I've connected this chamber to our airspeed indicator. Remember, nothing can flow into an airspeed indicator, it senses pressure, so it ain't going to get filled up with water or anything nasty like that. The water is in here, there's the water level, and all I have to do is raise this chamber up, which I can do using the vernier scale very accurately. I've leveled up the instrument on the table, the scale is vertical, and when I raise this chamber up, I'm going to create a difference in the two water levels. If the water can't flow, which it can't, into an airspeed indicator, I'm going to create some pressure. Now once I've done that, I may have to to get the needle back on a meniscus, I might just have to introduce some air to tweak the volume in the line to make up for the compressibility of the air in the line, but we'll deal with that in a minute. So 50 knots, 41.44 millimeters of water. So I am going to raise this up 41.44 millimeters using the vernier scale. Right, up we go, chamber and all. Now I need to put my vernier inspecting glasses on and bring you back when I've actually found 41.44. But I've raised it up 41 and a bit, and we've got very close to 50 knots on the scale, so we're in the right area. Alright, I'll bring you back in a second. Okay, now with my best vernier inspecting glasses on, I have set 41, alright, where are 41, a little over 41, there's the 0.4, 0.42, 0.44. It's a parallax free scale, that's pretty damn close. Verniers are always hard to read, but we have a smidge under 50 on our SI. But let's have a look at I need to turn the flash off, stand by. Let's have a look at the needle of doom if we can make it focus. Okay, it's dipped into the surface of the water. So, as we suspected, there we go, it's focused. We lost a little air due to compressibility, but I've got a little pump. In fact, I can probably just squeeze the tube. I'm squeezing the tube now. There we go, and the needle there is just right on the meniscus, and it's reflected its own image, and it's absolutely point to point. And if we look here, we have on the money, focus. 50 knots. Not a needle's width that. I'll have for the parallax there, get you square. And that's a good ASI, and that's what we need. I'll just try and get a shot in there how sensitive this thing is. There's the needle. I get it in focus, which I can't. It's actually quite hard to look down a viewfinder with a phone. There it is. As I squeeze the tube, I'm literally just squeezing the soft tube to fine tune the amount of air in the system. And it's very sensitive. See meniscus deflecting there, needles point to point, and then if you squeeze it too hard there's a gap between the two. So that is a very accurate way to measure the height of the surface of some water. I'll just put the flash back on. So that's it, we'll go over it quickly. The vernier water manometer. This chamber goes up and down on a vernier scale, so its height can be measured very accurately relative to the other chamber. And chamber here, connected, this chamber here, okay, connected by a tube. If we create a height difference between the two, it will either create a pressure or require a balancing pressure to bring this water level in this chamber back to the fixed needle, and we can, using the clever optical device and the internal reflection of the needle, we can very accurately set that needle on the surface of the water. So we have a very accurate way to measure the height of this water surface above this water surface. And that height is proportional to the pressure that is maintaining that height difference. It's a fixed thing, a known thing. It depends on gravity, the density of water, and the temperature. And it's not subject to the mechanical errors that any round dial instrument is subject to. There are no gears and whizzy bits inside it. Once the water is equalized and stopped flowing, there's no friction. So it's a really reliable, known standard that you can visually use to set, in this case, an airspeed indicator. And that's really important to know, that your instruments are, your test equipment rather, is reliable. If you ain't got good test equipment, you've got a big problem, because you'll get sooner or later a disagreement between an aircraft instrument and your test instrument, and you will not know which one is any good. And then you're screwed. Right, and that is why it is important that equipment used is calibrated, and that's why we spend time doing it. We know when an aircraft goes out the doors here, if we've checked its instruments, we've checked them against something that is certain as we can be. And if we have example pressure instruments using this manometer for stuff that's at low pressure, we are sure of our kit. We have a dead weight tester for doing some higher pressures, which I'll go through with you sometime. Again, this is dull and boring, but it has to be done. We have records here. I've taken readings after readings this morning, and in fact most of the day, of all our instruments, mics, measuring instruments, pressure gauges, torque wrenches, bits and pieces, against master standards which are provable, demonstratable, knowable, whatever the word is. This is the airspeed this morning, a number of instrument readings, the correct reading, the error, and the percentage error, and this is all recorded. If we have an audit, we can show that our instruments are right. But more importantly, with being able to do a bit of stuff in-house like this, if we have a doubt during the year that an instrument has gone up the creek, we can check it and go back and know that anything that we checked with it when it was defective can be dealt with. I was going to say, it's really important. Thanks for watching. Like, share, subscribe. Okay, whatever you're doing with test equipment in your workshop, if you have any doubts about that equipment, you need to get it calibrated because it is useless. Have a good evening. Good night.